Welcome to this lecture. In this week, we are focusing on the limiting behavior of measure theoretic integration, and we are also going to see applications of this in obtaining other measure properties. So, in the first lecture of this week, we have already seen a proof of the monotone class theorem, and as an application, we have seen a brief sketch of the proof of the additivity of the integration. So, we are continuing that discussion and we are going to look at the structures that follow when we focus on the limiting behaviors. So, let us move ahead and start the discussion with the notes. So, in this lecture, we are going to discuss the effect of null sets in integration. So, what do I mean by null sets? Null sets mean the sets of measure 0 in the given sigma field. So, for the purpose of the discussion, we are going to fix this measure space omega, script f and mu. First definition is about certain properties holding mu almost everywhere. What does it mean? Property p, script p is said to hold mu almost everywhere if there exists a null set in your sigma field. So, that means that it has measure 0 such that outside the null set, on the complement of the null set, the property p holds at that point omega. Okay. So, therefore, you are going to obtain some null set outside which you are going to get the required property, or you can verify the property on those points. Okay. So, a shorthand notation for this kind of a situation will be mu a dot e dot, mu almost everywhere. Okay. So, that will be shorthand notation that we are going to use. Alright, so let us first try to understand what do these almost everywhere statements look like and what do they mean. So, consider some function h, it need not be measurable, but suppose you know that there is a function h such that on the points where h takes negative values, that set has measure 0. Suppose you are given this fact, then you are going to say that h is greater or equal to 0, h is non-negative, mu almost everywhere. Alright. So, again on the complement of this set, you get the other condition which is h greater or equal to 0. Alright. So, that is what you are looking for. You are looking for such null sets outside which your property or the statement holds. Alright. A similar situation might involve two functions or more functions. So, let us look at this situation. So, again let us consider functions f and g. Again this need not be measurable as long as you know that the set of points where f of omega is strictly greater than g of omega, if that measure is 0, then what you say is that f is less or equal to g mu almost everywhere. Okay. So, therefore, as long as the measure of the complementary event gets 0 mass, okay, or if the complementary event is contained in a set of measure 0, then you are going to say that this happens almost everywhere. However, you have to introduce a separate terminology for the special case when you are dealing with a probability measure. So, suppose you are dealing with a probability measure and you are going to talk about these almost everywhere statements. So, instead of using this term almost everywhere here, what we prefer to use is the term almost surely, okay, or p a dot s dot. If the probability measure p is clear from the context, so once you have fixed it beforehand and then started the discussion, then you might just go with almost surely or a dot s dot. Okay, you don't have to mention the probability measure explicitly. But we are going to focus on such situations and we are going to look at what is the effect of such sets in integration. So, here is the first result. So, consider a measurable function now, call it h, its real valued function such that it's 0 almost everywhere. Okay. So, then we are going to claim that integration of h with respect to the measure mu is 0. So, So to prove such a statement, we are going to follow the usual procedure, the standard procedure, that you are going to work with indicators or simple functions. Then you go to non-negative measurable functions and finally to general measurable functions. So let's start with the case of a simple function. Okay. So let's see what happens here. So you have a linear combination where you have these scalars xi and these pairwise disjoint sets ai. So you have this linear combination. That's a standard representation for a simple function. Now if it so happens that for some value xi you have that is non-zero, okay, so suppose you have that, then you observe that the corresponding set ai will be contained in the set of points where h takes non-zero values. Why? First of all, ai's are taken to be pairwise disjoint. So therefore on the points inside ai, these indicator will only contribute, other terms will not contribute. So therefore on those points the value of h will be exactly xi, and if xi is non-zero, you get the value of h is non-zero there. So therefore if for some I xi is non-zero, then the set ai is contained in the set of points where h omega takes non-zero quantities. Okay, then use the fact that mu measure associates zero mass to such a set. You use that fact to claim that measure of ai is 0 whenever the xi is non-zero. So you have that conclusion. Now let's look at the integration of h. So as per definition, we have to make sense of this summation first, that you are going to multiply the scalars xi by the size or the measure of the sets ai. But here something interesting happens. Either the value of xi is 0, in which case the product is 0. Here we are using the fact that 0 times infinity is taken as 0. Otherwise, if xi's are non-zero, they are some real numbers, but you are multiplying sets of measure 0 here, right? So you are considering sets of measure 0 here. Measure of ai is 0. So therefore xi multiplied by the measure of ai will be 0, right? So therefore all the terms here are 0. If you sum them up, you still end up with 0. So therefore what you have obtained is that integration of h exists and is 0. So here we first made sense of this summation as per the definition. Let's move ahead and consider the case when h is non-negative and measurable. In this case, what do you do? Follow the definition. Take any simple function small s which falls between 0 and the function h. In this case, observe that the points where the simple function takes non-zero values, on the set of points h will also take non-zero values. Why? Because you are dealing with functions h and s to be non-negative, and if you know that s takes strictly positive values, so these are the points exactly where s takes non-zero values. So on those points h also must take non-zero values, as it is taking at least that much value on those points. So it is above the function s. Okay, so therefore you have this inclusion. But now since the set of points where h takes non-zero values, that set of points has 0 mass, you will immediately claim that the set of points where s takes non-zero values, that also has 0 mass. And hence you now apply the result that you have obtained in the previous paragraph for simple functions. You immediately claim that the integration of such a simple function must be 0. But you have chosen the simple functions to be below h such that it falls between 0 and h. And for all such simple functions, you have now claimed that the integration is 0. And integration of h by definition is the supremum of all these quantities, therefore it turns out to be 0. So therefore you have shown that integration of h, here it is defined and it takes the value 0. So let's move ahead to the case of general measurable functions, which takes now real values. So it can take positive values or negative values. So you follow the definition and split the function h into its positive part and negative part. So again observe that the set of points where h takes positive values, On those points, you know that h minus the negative part will be taking 0 value. This identification has been discussed earlier. Therefore, on the points where h plus is strictly positive, on those points h omega must be non-zero. Similarly, you can make the same statement for h minus, that the set of points where h minus takes non-zero values, it's contained in the set of points where h takes non-zero values. But you are given that the set of points where h takes non-zero values, that has measure 0, and hence you will claim that both for h plus and h minus, the set of points where these functions takes non-zero values, that has measure 0. But since h plus and h minus separately, they are non-negative and measurable functions, so therefore using the previous steps argument, you will claim that the integration of h plus and integration of h minus both must be 0, and hence as a difference of these two quantities, h will have an integral, so integration of h exists and takes the value 0. So you complete the proof for all the type of functions that you consider in measure theory. Alright. So one important step that we would like to highlight is that in the above proof, in each step we have established the existence of integration of h. Okay, and then we are showing that integration of h is actually 0. Okay, so let's just go back to the statement just to highlight this fact. So in the statement, we are not saying that h has integral or integration of h exists. We are directly claiming that we are starting off with a measurable function. So a priori do not know whether integration of h exists, but it is a part of the statement that integration of h exists and takes the value 0. Okay, so this clarification is important. Alright, good. So let's see what happens if you try to use this result and obtain further nice properties. So here you start off with two measurable functions g and h now, and suppose it happens that g equals h mu almost everywhere. So that means the set of points where inequality holds will be contained in a set of measure 0. Okay, so that's good. So therefore you can now try to say about their connection involving the integration of g or integration of h. So here the statement says that if one of the integrals exists, then so that's the other and they must be equal. So how do you show this? So suppose you start by assuming without loss of generality that integration of g exists. Then you consider the function f, which is g minus h. So g and h separately they are given to be measurable functions. So therefore their difference, which is f, is also measurable. But then you are given the fact that g equals to h almost everywhere, and therefore you will claim that f must be 0 almost everywhere. So therefore by the previous proposition you will immediately claim that the integration of f exists and it is 0. Now look at the fact that h now can be expressed as g minus the function f, and as such you are going to use the additivity property to claim that integration h d mu exists. Why? You have assumed integration of g exists and you have shown that integration of f exists. So therefore their difference makes sense and will imply the existence of integration of h d mu. Great. But then what is the value? The value is exactly the difference of the two integrations, but the second integration is nothing but 0. So therefore you get back the value of integration of g itself. So therefore if one of the integrations exists and the functions match almost everywhere, you get the same value for the other function's integral. So this is a very important property. Now you can try to extend this kind of a notion when you are dealing with extended real valued functions and their integrations. So suppose you consider g and h to be extended real valued and Borel measurable, then consider mu integrable functions. So again, here you are assuming that integration of mod h with respect to the measure mu is finite. Then the statement says that the set of points where mod h takes plus infinity as its value, that has measure 0. Okay. So, and restatement of this in terms of the function h is this, where the function h takes plus or minus infinity as its value, that set has measure 0. Now, there is a way to state this in terms of almost everywhere statements, and you are going to say that h is finite mu almost everywhere. By that we mean that h takes these infinite values plus or minus infinity on sets of measure 0, or such possibilities are included in a set of measure 0. We prove this by contradiction. So assume that the set of points consisting of the situations where h of omega takes infinite values, so that set of points, if it has positive mass under the measure mu, then consider the integration of mod h. So here mod h is a non-negative function and therefore its integrals exist could be plus infinity. But let's look at this lower bound. So we consider the multiplication by this specific indicator. Okay. So this is exactly the set where mod h is taking value plus infinity. Alright. So we are just multiplying by this indicator and therefore mod h is greater or equals to mod h times this indicator. So we are using that inequality for the integrations. But on this set, mod h takes the value plus infinity. So it's just a simple function here. So you get this value for while you compute the integration as per the definition. So this is the value of the function multiplied by the size of the set, and that turns out to be infinity since the measure of this set is assumed to be positive. Therefore, we ended up with the fact that integration of mod h is infinity, but this will contradict the fact that h is integrable. Remember, h is integrable means that integration of mod h is finite. So we have a contradiction which arises from this condition which we assumed that this set of points has positive mass. So therefore this set of points must have 0 mass, and that will tell you or give you the result. Okay. So let's move forward and use this observation in the next result. Consider a non-negative function h now. So then you can always consider the integration of h, but if it so happens that the integration of h is 0, then we can claim that h is 0 mu almost everywhere. So again, how do you approach this? So it is given that h is non-negative, so you don't have to worry about h taking negative values. So forget about that situation. So now we only have to consider two situations when h takes the value 0 and h takes positive values. Okay. So now you want to show that h is 0 mu almost everywhere. So it is therefore enough to show that h takes positive values on a set of measure 0. Okay. So that's the target. Now this set, instead of directly working with it, consider a slightly different set. So for integers n 1, 2, 3, 4 and so on, consider this sequence of sets where h takes the value greater than 1 by n. Okay. So you just consider this set of values. So we first claim that this set has 0 mass under the measure mu. If the claim is true, then observe that the set h taking positive values, that set has this approximation from below by the sets h greater than 1 by n, right? So that's all you have to observe and use the continuity from below of the measure mu. Now if it so happens that mu assigns mass 0 to h greater than 1 by n type sets, then the limit value is also 0, and that will tell you that h takes positive values on a set of measure 0, right? So that's will end the argument as soon as you prove the claim. Alright, so you want to prove that for all natural numbers n, h greater than 1 by n, that set of points will get 0 mass. Again, use a contradiction argument. Okay, so this is a proof by contradiction. So suppose for some natural number n naught, it so happens that the measure of this set is positive. Then try to compare the functions h and h times the indicator of this set, right? So here we have assumed that the measure of this set is positive. But observe that h is non-negative, so therefore inequalities pointwise holds, and therefore the same inequality holds for the integrations. But on this set h takes values greater than 1 by n naught, so you get this lower bound for the integration. Remember, it's always greater equals to here. Alright, so now you put that lower bound here 1 by n naught and then consider the indicator function. So that's all we are writing down. But then this is now a simple function. Write down the integration, so that is positive. Okay, so now what does it tell you? It says that integration of h is strictly positive. Okay, so that will contradict the hypothesis, and therefore this contradiction is arising from the assumption that for some natural number n naught, measure of this set is positive. Okay, so therefore we must have that for all possible natural numbers, measure of h greater than 1 by n is 0. Okay, so we must have that. Now you use this while comparing two functions. So if it so happens that you take two measurable functions h and g, and you observe that modulus of h minus g, that's a non-negative function, integration of that is 0, then you will claim that h equals to g mu almost everywhere. Okay, so how do you prove this? So here you take the function f to be modulus of h minus g. So this is now a non-negative function which integration is 0, right? So therefore by the previous part you will immediately claim that f must be 0 mu almost everywhere. But that will immediately tell you that on this set of points where the function f is taking value 0, there you must have h equal to g. That's pointwise happens. So therefore outside the appropriate null set you must have h equal to g. So that completes the proof. Great. But now here is an interesting question. So suppose it so happens that instead of assuming that h is non-negative throughout, you assume that h is non-negative mu almost everywhere, and take it together with the fact that integration of h is 0, then can you show that h is 0 mu almost everywhere? So this is the only difference in the hypothesis now, that we had earlier assumed that h is non-negative throughout, but now we are saying h is non-negative mu almost everywhere. But we are taking the integration of h to be 0, then can you now claim that h is 0 mu almost everywhere? Take it as an exercise. But an important fact that we have understood from all this discussion is that the values of a measurable function on a set of measure 0 will not affect the value of the integration. Okay, so you can forget about the values of the function whatever they are on a set of measure 0. And more generally, in the setup of this proposition where we had done all these computations of functions and so on, if we are only interested in the integration part, then the equality g equals to h mu almost everywhere may be treated as a equality of functions. So let's just go back to this proposition 2 once more. So in proposition 2 we stated that if two functions are measurable and they agree almost everywhere, if one of the integrals exists, then so does the other, you also get the equality of the integration. So if you are only interested in the equality of the integration and existence of the integration, then you can as well treat the functions g and h to be the same in this setup. So if two functions agree and you are only interested in the integration value, then you treat the two functions to be the same. So in the setup of this proposition 2, you are going to consider that two functions agreeing almost everywhere is almost equivalent to a equality of functions. Okay, all right. But we have also mentioned in proposition 3 that you can talk about this extended real valued functions, but if they are integrable, then this is essentially real valued. So we said that this is finite valued, right? Finite valued means it's real valued. So therefore it can only take the values plus or minus infinity on a set of measure 0. It cannot take plus or minus infinity on a set of positive measure. Okay, so therefore here also you can treat it as a real valued function as long as you are dealing with integrations. Okay, so as long as the function is integrable, then the function cannot take plus or minus infinity as its value on a set of positive measure. Okay, great. So with that understanding, let's now consider the case of random variables. So we have so far discussed the situation for general measurable functions, but suppose you want to discuss things when the given measure is a probability measure. So highlight that probability measure here and you consider a random variable x. If it so happens that you get this bound pointwise, that there exists a constant c positive such that mod of x omega is dominated from above by this constant for all points, then you get this bound for the integration and therefore the expectation. So expectation of mod x is integration of mod x with respect to the probability measure p, but if the function mod x is dominated from above by this constant function c, you observe these inequalities and find that expectation value of mod x is finite. So therefore x is integrable in this situation. So if x is bounded by such constants, x is integrable. However, in the discussion above, we have considered this kind of inequalities in the almost sure framework. Okay, so whenever you are talking about probability measures, you talk about, instead of saying almost everywhere, you say almost surely. Okay, so the a dot s dot. Great. So suppose this happens, then for again an appropriate p null set, you get these appropriate statements that this domination holds. But what happens to this inequality now? Okay, so here you already have a bound on n complement. So if n is the null set, then on the complement of the null set you get the bound. So that's what almost surely statements imply. But you can consider this inequality that mod of x omega is less or equals to c times the indicator of n complement plus infinity times indicator of n. Observe that this inequality holds now pointwise for all points in the domain. Okay, now try to look at the bound function here. So here you are using the constant value c on n complement and the value infinity on the set of measures 0 n. Okay, so now try to show that this upper bound that you have constructed, this function is integrable, and that will tell you that x will also be integrable. Okay, so verify that x is integrable if x is bounded from above by a constant almost surely. Okay, so you can reduce this restriction that it has to be bounded pointwise to bounded almost surely. Okay, so try to work this out. This is left as an exercise. Okay, so now here is an interesting comment. So look at this very specific situation that omega is a 3 element set ABC and consider the Dirac measure supported at the point C here. Okay, now specially you consider this sigma field scripted f here, which is made up of these 4 sets: empty set, the doubleton set AB, singleton set C, and the whole set omega. These 4 set. Okay, so you can immediately verify that this is a sigma field. Now consider the Dirac measure here and consider these two special functions. So g and h. So g is taken as indicator of the set, the doubleton set AB. Okay, but take the function h like this, that you define the function value h at the point A to be 1, at the point B to be 2, at the point C to be 0. Okay, so we will see the reason for these choices. Now observe here that the Dirac measure supported at the point C will not put any mass on this doubleton set AB, right? So that will be 0. Here one important comment is that we have not included the subsets singleton set A and singleton set B in the sigma field. So remember, our sigma field is made up of the empty set, the doubleton set, and this singleton set and the whole set omega. So the singleton sets A or B are not there in the sigma field. Okay, so here I have this set of measure 0, which is this doubleton set, but its subsets A and B singleton sets are not included in the sigma field. Okay, so what we have observed is that subsets of null sets, here the doubleton set is a null set, the subsets of it need not be in the sigma field. So this gives you a interesting observation. But now consider this situation for the set of points where g and h does not agree. So again, let's just go back to the values of g and h. So g takes the values 1 on the points A and B, takes the value 0 on the point C. Okay, so therefore g and h differs only on the point B. All the other points A and C, the functions g and h match. So only at the point P the functions do not agree. So if you consider this set of points where G and H do not agree, so that will be the singleton set B. But this is the subset of this null set that we have just observed. But this specific null set is not having this property that all its subsets are also in the sigma field. Okay, so specifically this subset singleton set B is not included in the sigma field. Okay, now by definition G equals H almost surely. Dirac measure is a probability measure, so you use the term almost surely. Okay, so it does not agree with this function H only on a set of measure 0. Okay, so you can as well consider this set AB, that will be a superset of the points where G and H do not agree, and the superset has 0 mass. Okay, but here you note that G, which is indicator of the doubleton set AB, is measurable because the doubleton set is in the sigma field, but H is not a measurable function. So observe this, that G is measurable, G agrees with H almost surely, but H is not a measurable function. Okay, so this is an important observation. Okay, so please check this. So in continuation of this observation, given a measure, we usually are going to enlarge the sigma field by including all subsets of null sets. Okay, so typically it may not be true that all subsets of a null sets are already included. Okay, now if you include all these possible subsets of null sets, this procedure of enlarging the sigma field is known as the completion of the sigma field. So by including all the null sets and by an appropriate construction, you can get a sigma field once more, which will be containing larger number of sets. Okay, all right. Now this is known as completion of the sigma field with respect to the given measure. Okay, so here what we are considering is the Dirac measure here, and we had observed that the singleton set B was not there. If you include this by considering that these are subsets of measure 0 sets under the measure Dirac supported at C, that will be the completion. Okay, if you include all those appropriate subsets. So here we are not going to discuss this topic in further detail. We shall, however, briefly connect this topic in a later lecture. There we are going to talk about the Lebesgue measure on the Borel sigma field. So take it as a fact that the Borel sigma field is not complete with respect to the Lebesgue measure. By that I mean not all subsets of null sets are included. And what we are going to do is to include all the subsets of measure 0 sets included in the Borel sigma field. And if you include all those subsets which are subsets of measure 0 sets, you are going to enlarge the Borel sigma field, and you are going to get a sigma field by an appropriate construction that is referred to as the Lebesgue sigma field. This later sigma field now contains all subsets of the null sets with respect to the Lebesgue measure. Okay, we are going to use this sigma field in a very specific construction, but otherwise we are always going to work with the Borel sigma field. So we are assuming the fact that Borel sigma field is not complete with respect to the Lebesgue measure. By that I mean not all subsets of measure 0 sets are included. Okay. However, we are not going to discuss the completion structure, the procedure of completion in further detail. Okay. All right. So we stop here and we will continue the discussion in the next lecture.